Hello and welcome to the week 5 review for Math 2419. Today we'll be covering some vector valued functions. We'll start off with just a brief introduction, then we'll talk about differentiation and integration of those functions, and lastly we'll discuss a little bit about velocity and acceleration in terms of vector valued functions. So let's go ahead and get started. All right. With the basic definition of a vector valued function. So a vector valued function takes input of a real number and it maps it to a vector. You might see it something like this, where our function r of t takes in a t value as input right there, and the output is some vector r. You can see it written in the form f of t, g of t, h of t, where the vector components are functions of t themselves. So you might also see it written as f of t times your first unit vector I hat plus g of t times your second unit vector j hat plus h of t times your third unit vector k hat. So that is one way you might see your vector valued functions written. And a vector valued function is basically, you can think of it as the space curve traced by the tip of the vector f of t, g of t, h of t. So this vector, you can think of it if we were just looking at 2 dimensions. Then we have some kind of vector valued function. We'll call this line right here our r of t. Then at any point on this space curve, we would be able to draw a vector from the origin to the point, like so. And what's going to happen is, as this point on the space curve moves, that is always the tip of the vector. So you can imagine our vector valued function just being the space curve traced out by the very end of this vector, and it'll follow along the space curve just like that. So because you can trace it out in a direction, vector valued functions do have a direction, just like parametric curves. And you'll actually see that there's a lot of similarities between vector valued functions and parametric curves. So let's get into a little bit of the nitty-gritty of vector valued functions. If you wanted to look at limits with vector valued functions, you're going to need to look at everything purely component-wise. For instance, if you wanted to take the limit as your t value approaches some value a of f of t comma g of t, and of course you could have more components, but I'm not going to list them. Well, this limit is simply the limit of each component. So on. You just do it to every single component. So for example, you could take the limit as t approaches to 2 of the vector valued function t squared comma 4t comma 2 minus t. And all we do is we take the limit component-wise. So the limit as t goes to 2 of t squared is 4. The limit as t goes to 2 of 4t is 8. And the limit as t goes to 2 of 2 minus t is 0. So this would be our answer. If we wanted to do a bit more complicated of a limit, consider the limit as t approaches to 3 of t natural log of t and then 1 over 3 minus t. Well, if we broke things down component-wise, the limit as t goes to 3 of just t is 3. Then we'd have the natural log of 3. And lastly, we would have the limit as t approaches 3 of 1 over 3 minus t. But this final limit does not exist. And if one of these component limits does not exist, we have to say that the limit of the whole vector-valued function does. So I'll go ahead and give you guys a practice problem. Go ahead, take a minute to work it out. It'll be the limit as t goes to 0 of natural log of t plus 1 over t, tangent of t, go ahead, take a minute and work that out. All right, let's go ahead and go over this problem really. Remember, when we're taking the limits of vector-valued functions, we need to break it down component-wise. So our answer would be the limit as t approaches 0 of the natural log of t plus 1 over t, comma, the limit as t goes to 0 of tangent of t, and lastly, the limit as t approaches 0, square root of 4t plus 3 over 7 cosine of t. And our second and third components we can get just by plugging in 0 for t. We would get 0 for the second component and the square root of 3 over 7 for our final component. Our first component, if we just plug in 0 though, we get natural log of 1, which is 0, divided by 0, and this is an indeterminate form, so we have to apply L'Hopital's rule here. And we would say that this is equal to the limit as t goes to 0 of, now we get 1 over t plus 1, the derivative of the top, divided by 1, which is the derivative of the bottom. And if we plug in 0 here, we get 1 over 1 over 1, which of course gives us 1. So our final answer would be 1, 0, square root 3 over 7. Make sense? All right. So we'll move on from limits of vector-valued functions and start talking about when a vector-valued function is defined. So a vector-valued function is defined only where all of its components are where all of its components are defined. And this really isn't too difficult of a concept. We'll just do an example to illustrate. Let's say we wanted to find the domain of this vector-valued function, natural log of t plus 1 over t, comma, tangent of t, comma, 4t plus 3 divided by 7 cosine of t. This is just the example from the previous limit problem. All right. Well, we need to identify where each component individually is defined. For this first component, well, we know that we can't divide by 0, so we know that t is not equal to 0, and also natural log has to take in a positive number. So t is also bigger than -1, and that gives us, for our very first component, the interval -1 to 0 combined with the interval from 0 to infinity. For our second component, well, tangent is sine divided by cosine. We can't divide by 0, so anywhere where cosine of t is equal to 0, we can't have in our domain of our vector-valued function. So that tells us that the domain of tangent of t would be all real numbers except for the numbers that look like an integer multiple of pi plus pi over 2. And this might look a bit complicated, but basically this would contain all the values where cosine of t is equal to 0. If we let k equal to 0, we would get pi over 2. Cosine of pi over 2 is equal to 0. Likewise, if we let k equal to 1, you get 3 pi over 2. Cosine is also 0 there, and k is 2. 5 pi over 2, same thing. Next, we need to look at this final component. And of course, we have a couple of constraints here. First off, we're dividing by cosine again. So let me just make a note. We again cannot have k pi plus pi over 2. But then we also have to have a positive under our square root. So we know that 4t plus 3 has to be bigger than or equal to 0. And that tells us that t is bigger than or equal to -3 over 4. All right, so then the total domain of this whole vector-valued function would be where all of these overlap. So we can look at t is bigger than -1 and say, well, t is bigger than or equal to -3/4 is more constrictive. So we need to start with -3/4. We go up to 0, but we know we can't include 0 because 0 is not allowed for our first component. But then we also can't have any value that takes this form. Any value that would make cosine of t equal to 0. So we can say that our t value has to be either between -3/4 and 0, or from 0 to infinity, and it cannot be of the form an integer times pi plus pi over 2, and that would be our total domain for this vector value function. And this one might look a bit complicated, but really if you break everything down into steps, just identify the domains of each component and then find where all of those overlap. It's not that difficult. Right. I'll go ahead and give you guys this problem. Go ahead or a couple of practice problems. Your job here is just to find the domain of these vector valued functions. And here's the first one. We'll start it off with one. And I'll give you a couple of minutes to work on those. All right, let's go ahead and go over these really quick. First off, we look at the first one, the very first component, 3t, as a domain of all real numbers. The second component, well, if we factor the denominator, this would come out to be 2 over t plus 1 times t minus 1. And then we could clearly see that t could not be equal to -1 or +1. Oops. And finally, for our final component, since our denominator can't be 0, t is not equal to 0. And if you combine all of these, we get that t is not equal to -1, 0, or 1. So we can write that the domain of t is -infinity to -1, combined with -1 to 0, combined with 0 to 1, combined with 1 to infinity. All right. For the second one, we need to take a look at where the square root of t, the domain of square root of t, and this is all positive numbers. So we'll start with, so we will start with 0 inclusive and go up to infinity. The domain of arcsine is, let's see, so I'm blanking on the domain of arcsine. I believe it is -π/2 to +π/2. I'll just double check that really quick. Right, actually the domain is -1 to +1. So good thing I double checked. And that would be inclusive. So it takes values from -1 up to +1. And lastly, this final component, in order to make the sign under the square root positive or 0, we would need a negative or 0t. So it would be -infinity to, that should be a 0, and inclusive. And if we look at where these overlap, well, -infinity up to 0 only overlaps with 0 to infinity at the point exactly 0. So our domain would just be the single t value of 0. And not a very helpful function there. Finally, for our final component, our final vector valued function, the first component, e to the -t, can take in any t value. E to the 4 square root t squared. Well, in order to make the sign under the square root positive or 0, since we have a t squared, t can once again be any real number. So lastly, we just need to make sure that the natural log of the absolute value of t minus 7 is bigger than 0. Now, we can write our, then we get that the absolute value of t is bigger than 7, which tells us that either positive t is bigger than 7 or negative t is smaller than -7. Remember, we have two options with an absolute value. We can split it into the positive component, which is what I've done here, but then also the negative component. And with this negative component, I needed to flip the sign. And of course, we can double check this really quickly. That should be, well, to clarify this, we have that negative t is also bigger than 7, which tells us that t is less than -7. If we divide by the negative, that's when we have to flip the sign. So there you have it. This tells us that we have a domain of -infinity to -7 from the second component. The t is less than -7, or t is bigger than +7. That would be 7 to infinity. And since both of our first two components gave us domains of all real numbers, then the only restrictions would come from this final component of our vector valued function. So our domain is -infinity to -7, union 7 to infinity. All right, I believe that's enough looking at the domains. So we'll move on to some differentiation and integration. And a lot of this is Has parallels with the limits or finding the domain of your vector valued functions. Basically, whenever you differentiate a vector valued function, you're going to differentiate each of its components. So if we have a vector valued function r of t, well then we could say the change in our function with respect to t would just be the derivative of each component. And of course, this is if our vector valued function is defined like a function of t, a function of g, and then a function of h. So when you take the derivative, just take the derivative of each component individually. And a quick example, we wanted to take the derivative of cosine t, sine t, t. Well, all we do, take the derivative of cosine t, we get negative sine t. Derivative of sine t is cosine t, and derivative of t is just 1. So that would be our derivative. Now, one quick practice problem. Go ahead and try taking the derivative of this vector valued function, natural log t squared plus 1 cosine of t and arctangent of t. All right, let's go ahead and take the derivative. Take the derivative component-wise. Derivative of natural log t squared plus 1 is going to be 1 over t squared plus 1 times the derivative of the inside, so times 2t, comma negative sine of t. And the derivative of arctangent is going to be 1 over t squared plus 1. Now, quick definition to review. A vector valued function is smooth. So I'm going to write that r of t is smooth on an open interval. And this is just some region. We'll call it I if it is 1 continuous on I and 2 the first derivative is not equal to the 0 vector on I. So for example, we have a vector valued function r of t equals to 4e to the 2t cosine of t and then 2t. We could see, first off, we need to find where r of t is continuous. And for this first component, that's all real numbers. Second component, once again, all real numbers. Third component, all real numbers as well. So the domain of r of t is all real numbers. Next, we need to take the first derivative, and we see that it is 8e to the 2t, negative sine of t, comma 2. And we can say that this is never going to be equal to the 0 vector because, well, first off, this 2 right here is a constant. Oops. 2 right here is a constant, and it's never going to be equal to 0. But also, 80 to the 2t is also never going to be equal to 0. So because r prime of t, our first derivative, is never equal to 0, then it is smooth on the whole interval where it is continuous. So we can say that r of t is smooth for all real numbers because r is continuous on all real numbers. Let's do another example. Let's say you have r of t is equal to a constant vector, 1, 4, 7. Well, obviously, the domain of R is going to be all real numbers since there's no restrictions on the domain. We can say that the domain is all real numbers. But when we take our first derivative, well, the derivative of a constant is just going to be 0. So no matter the value of t, we can see that the first derivative would be equal to 0. So that tells us that R is not smooth anywhere, because for all values of t, the first derivative is equal to 0. All right. How about a couple practice problems? Let's say you have first off, see where this function is smooth. For either t squared, cosine of t, and t cubed. And secondly, see where this function is smooth. I'll give you a couple minutes to work that out. All right. Let's go ahead and go over this. First off, if we look at the domain of our first vector valued functions, we could see that it is all real numbers. So we need to take the first derivative. We get or e to the t squared times the derivative of t squared, which gives us 8t e to the t squared. Next, the derivative of cosine is negative sine of t. Lastly, we get 3t squared. And we can actually see our first component is going to be 0 only where t is equal to 0. But then if we plug in t is equal to 0, we can see that r prime of 0 actually gives us 0, 0, 0. So r of t is smooth wherever t is not equal to 0. So that would be the interval from negative infinity to 0 combined with 0 to infinity. All right, for this final one, first off, we need to consider the domain. First component has a domain of 0 to infinity. Second component has a domain of all real numbers. Third component has a domain of -1 to +1 inclusive. So our total domain is the interval from 0 to +1 inclusive. Now, when we take our first derivative, we get 1 over, oops, need my brackets, 2 square root t, 3, and then 1 over the square root of 1 plus t squared, I believe it is. And let me double check that. Whoops, that should be -1 over, I was wrong there. That needs to be -1 over 1 minus t squared. Perfect. Now, we can see that because of this 3 component in the middle, this vector is never going to be equal to the 0 vector, because 3 is never going to be equal to 0. But remember, we defined smoothness on an open interval. This is a closed interval, so we can say that a function is smooth on the open interval from 0 to 1. We can't include those endpoints. That would be our answer. All right. As far as integrating vector valued functions goes, well, you basically integrate component-wise. So if we wanted to take the integral of r of t, that would be the integral of f of t dt, integral of g of t dt, integral of h of t dt, and so on. Now, one important note is that you might end up with actually several different constants. So you would end up with a plus c here, plus c here, and I'm labeling them as different constants because they may not be the same. For example, let's do a quick example. We have integral of cosine of t, 1 over square root 1 minus t squared, then 2t. Well, we simply integrate component-wise, so the integral of cosine is sine of t, but then we have to add our first constant. This second component is the integral, it comes out to be arcsine. This is a definition you should have memorized. Again, we have a different constant, and finally, the integral of 2t is t squared plus a third constant. It's important that you get all of those constants. So this would be the integral. Perfect, perfect. All right, now let's talk about some velocity and acceleration. And these are going to use some of the differentiation and integration rules you had. So velocity and acceleration. basically, if we let r of t, our vector valued function, be a position vector, well then the velocity vector v of t would be equal to the first derivative. And our acceleration would be equal to the second derivative, which also happens to be the derivative of velocity. And lastly, we could denote speed to be the magnitude of our velocity vector. And one thing to notice is speed is not a vector, it is a scalar, meaning it's just a single number. In this case, it might turn out to be a function of t as well. And we'll go ahead and do a couple of examples just to really illustrate these. And with this one, I'm going to take a position vector, cosine of t, sine of t, t. And from this, I can use it to find the velocity, the acceleration, and the speed. So the velocity would be equal to negative sine of t, cosine of t, 1. The acceleration would be the second derivative of position, or the derivative of velocity. I'll just label these. This would be negative cosine of t, negative sine of t, 0. And lastly, I can find my speed by taking the absolute value of velocity, or not the absolute value, the magnitude. So that would be the square root of negative sine t squared plus cosine of t squared plus 1 squared. This comes out to the square root of sine squared plus cosine squared plus 1, which is the square root of 2, which gives us our speed. In this case, the speed is a constant. It won't necessarily always be that way, though, as you will see in this next example. Actually, in this example, so let's say we have a velocity vector, and it looks like e to the t, cosine of t, and 1 over t plus 1. And we have a starting position, initial position of 1, 2, 3. And it's our job to find the position vector. Well, we know that our first derivative of position is velocity. So that tells us that our position vector would be the integral of our velocity vector. So when we integrate our velocity vector, we simply integrate each component. The integral of e to the t is again e to the t. We have to add our first constant. The integral of cosine is sine of t, plus a second constant. And lastly, we get natural log of t plus 1 plus a third constant. And I suppose that there would be absolute value bars in here. But it's not super important. Now we need to find the values of these constants because we're given an initial position. An initial position, that tells us that t is equal to 0. So when we plug in 0 for t, we get 1 plus c1, c2, natural log of 1 is 0, so c3, and this should then be equal to 1, 2, 3. Now looking at things component-wise, 1 plus c1 is equal to 1, So C1 is equal to 0, C2 is equal to 2, and C3 is equal to 3. So that tells us that our position vector is going to be e to the t sine of t plus 2 and natural log of t plus 1 plus 3. All right. And if we wanted to look at what the speed was, well, the speed would be the magnitude of the velocity. So our velocity is e to the t, comma cosine t, comma 1 over t plus 1. So our speed would be the square root of e to the t squared plus cosine of t squared plus 1 over t plus 1 squared. And we can't really simplify that a whole lot. I think the best we could do is e to the 2t plus cosine squared t plus 1 over t plus 1 squared. And this would be our speed. I'm just going to note that using a cursive s. But in this case, you can see we have a non-constant speed. That's just really one thing I wanted to show you. Speed will not necessarily always be constant. All right, one final practice problem. And then we'll call it. If you know your velocity vector is going to be equal to, let's say, actually, go ahead and give you an acceleration vector. You know that your acceleration vector is equal to e to the 2t, 0, 4. And also know that your initial velocity is equal to 5 halves, 0, 2 over 2, negative 4, and your initial position is equal to 3/4, 6, and 1. And I'll give you a couple minutes to work that out. All right, let's go over this. So to start off with, we can find our general velocity vector by integrating our acceleration vector. And when we integrate, we get 1/2 e to the 2t plus c1. The integral of 0 is just a second constant. And lastly, we get 4t plus the third constant. And when we plug in 0, we would get 1/2 plus c1. Then we would get c2, and lastly c3. So this would be equal to our initial velocity vector of 5/2 to -4, which tells us that c1 is equal to 2, c2 is also equal to 2, and c3 is equal to -4. So our velocity vector without constants, or with our constants replaced, would then be written as 1/2 e to the 2t plus 2 to 4t minus 4. Perfect. Now our position vector would then be the integral of the velocity vector. And if we integrate this velocity vector, we get 1/4 e to the 2t plus 2t plus a different constant. Once again, we'll call this one, I'm tired of using c's, so we'll use d1. And we have 2t plus d2. And lastly, 2t squared minus 4t plus d3. Now, we are again given an initial, this should be an r of 0, our initial position. So we can plug in 0 for t, and we get 1/4 plus d1, d2, and finally d3 being equal to 3/4, 6, and 1. So this tells us that d1 is equal to 1/2, d2 is equal to 6, and d3 is equal to +1. So now we can finally write out our full position vector to be 1/4 e to the 2t plus 2t plus 1/2, 2t plus 6, 2t squared minus 4t plus 1. This would be our final answer. Anyway, thank you all for watching and have a great day.